Problem 26 says we have a very large horizontal non-conducting sheet of charge with a uniform charge per unit area, sigma equals 5 times 10 to the negative 6th coulombs per meter squared. So this is our infinite sheet of charge. When I say very large, they basically mean infinite. Sigma equals 5.00 times 10 to the minus 6 coulombs per meter squared. So this is our charge density in 2D, represented by sigma. Exact same thing as rho, exact same thing as lambda, but it's 2D, so it's per area instead of volume or length. Cool? All right, so a small sphere of mass m equals 8 times 10 to the negative 6 kilograms and charge q is placed 3 centimeters above the sheet of charge and then released from rest. So up here we have a ball, some mass m, some q. M was 8.00 times 10 to the minus 6 kilograms, and we don't know what the charge is, but we do know that it's a distance 3 centimeters above the sheet. Alright, so it's released from rest, so we know that its initial velocity is 0 meters per second. I feel like that's going to be relevant later. Okay, so if the sphere is to remain motionless when it is released, what must be the value of q? Okay, so if we're going to release this mass and it's not going to fall, that means that the force that the sheet puts on the mass has to counteract its weight. So if we draw a free body diagram for this, there's our guy. We've got gravity pulling him down, and we need that electric force to push it up. So our electric force needs to be equal to mg in order to keep this guy from falling down, right? So our electric force is given by QE, which is our electric field. So if the sphere is to remain motionless when it is released, what must be the value of Q? So we're solving for Q. So Q is just mg divided by the electric field. So let's figure out what the electric field is for the sheet of charge. Now, we can be cheaters and look in the back of chapter 22 and just look up what is the electric field due to an infinite sheet of charge, but I feel like this is a good time to walk you through the Gaussian pillbox and how to figure this out for yourself in case you forget. So, kablam! Welcome to the Gaussian pillbox tutorial. Dun 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 dun. This is what we call it. I don't know why, because it looks like a little box, I guess. Alright, so if we take a cross-sectional view of our sheet, looking at it like this, our electric field for a positive sigma comes out like so. So it looks just like a line charge when you're looking at it from the side, but it's a sheet, not a line. Alright? So from our handy dandy Gauss's law, E dot dA equals Q enclosed over epsilon naught. Alright, so like we were talking about in problem 21, the whole point of using Gauss's law is to get this E outside of this integral. The only way we're going to be able to do that is if we choose a Gaussian surface such that E is constant along the entire thing. So if I have a nice sheet of charge, my electric fields are coming out like this. It's pretty safe to say that a constant electric field is going to occur parallel to the sheet. So I'm going to draw my little box that eats a chunk of the sheet. Chomp, 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 chomp. I'm going to make this really thick so you can like actually differentiate it from the sheet. Alright, so this is what it looks like from the side. If we're looking at it from the top, this is basically like just taking a hole punch in our sheet. Cool, cool. So just like a roar. Now you can do any shape box you want. You can do a circular box, you can do a cubic box, you can do a rhomboidal box, you can make it a blob for all I care. Any area you want, you can make your box. The only thing we give a crap about is, are the caps of my box parallel to my sheet? Because they need to be parallel so that the electric field is constant. That's it. So in my happy box, my electric field is coming out of my sheet like so. My dA for my caps is coming out parallel to the electric field. So for the caps, in this case, this is different from the line charge because the caps canceled in that one, but the caps are what matter here. The edges of my box, the walls of my box, my dA is coming out this way. So E dot dA for my walls is 0 because they are perpendicular to each other. So we'll say caps. E is parallel to dA. Walls. E is perpendicular to dA. So our walls don't contribute because their dot product is 0. So E dot dA equals 0. And here for my caps, E dot dA equals EDA. Cool? All right. So now we have our box. It has caps. It has 2 caps and a bunch of walls. Walls don't contribute. So forget about the walls. So in my E dot dA, they're parallel for my caps. So I can just say E times dA. So the closed integral of E times dA. And remember, the whole point of drawing a Gaussian surface is so that the electric field is constant all across your Gaussian surface, which for my caps is true. So I can pull my E out and get EDA. So that's going to be E times the surface area. Now, the surface area for this Gaussian pillbox, I have 2 caps. 2 caps. Cap on top, cap on bottom. So I have 2 times the area of my caps. And my Q enclosed is going to be sigma times the area that I punch out. So I'm punching out a little hole in my sheet. There's only one area in this one because there's only one sheet. 2 caps, 1 sheet. 2 caps, 1 sheet. So the A doesn't matter. Like I said, you can make this area of your box whatever the hell you want as long as the caps are parallel to the sheet. Alright? So my A's cancel out. My electric field, due to an infinite plane of charge, is sigma over 2 epsilon naught. So that's where that comes from, and you can see that at the end of your chapter. Okay, back to the problem. So my electric field is sigma over 2 E naught. So if I get the charge, my charge is going to be mg over E. Mg over E, and my E is sigma over 2 epsilon naught. So plugging in my numbers, I get 2. My mass is 8.00 times 10 to the minus 6 kilograms. Gravity is 9.81 times, there's no times 10, whoops. Meters per second squared. E naught is 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared over sigma, which was 5.00 times 10 to the minus 6 coulombs per meter squared. So if we stuff that into our handy dandy calculator, we get this many coulombs. Now for part B, it asks if you are 1.5 centimeters away, what's the charge going to be? If you'll notice, there is no position dependence for an infinite sheet of charge because it's really big. You can get a little bit closer to it and it's still really, 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 really big. If you can get really far away from it and it's still really, 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 really big. It's always going to seem as if it's closer than it actually is.